we were looking at embedding theorems. So we want to show, so when p is less than n, we showed that mod u 0 p star Rn was less than or equal to c times mod u 1 p Rn for all u in w1p of Rn 1 less than or equal to p less than infinity, okay, and 1 by p star equals 1 by p minus 1 by n, so that p star is greater than or equal to p. Okay, so how did we prove this? We first proved this for u in d of Rn, and then for some t greater than or equal to 1, we showed that mod u 0 Tn by n minus 1 Rn power t is less than or equal to t times pi of I equals 1 to n of okay, so after simplification we showed that this was less than t mod u 0 p dash t minus 1 Rn and power t minus 1 and pi I equals 1 to n of mod du by dxi 0 prn power 1 by n, and then we chose t suitably so that this became p star, and this index here common to both sides was equal. We chose t like that, and that turned out to be exactly p star, and therefore we then cancelled one mod u power t minus 1 on both sides, and we got the inequality. So now we want to consider, and then we pass to the limit using the density of d of Rn in W1p of Rn. So now we want to consider the case p equal to n. Now if p equals n, then of course p star, as p approaches n, you have that p star tends to infinity. Okay, when p actually becomes n, it becomes p star becomes infinity. So we will see what the theorem is now. So theorem, let p equals n. So we are equal to the dimension of the space, and we have then the continuous inclusion W1n Rn p equals n continuously embedded in LQ of Rn for all q belonging to n infinity. Infinity is not included. If omega equals Rn plus or has boundary and is of class C1, star holds for omega in place of Rn. If omega in Rn is any open set, we also have W1n0 omega is continuously embedded in LQ of omega for all q in n infinity. Okay, so the last part of the result follows directly from Rn using the hypothesis of precisely saying that you have an extension operator, and therefore you can apply the result in Rn and restrict it to omega, and therefore all this can be proved. So it is enough to prove when so proof enough to prove for Rn. So all the rest follows just because of the existence of extension operators. Okay. So let again u belong to D of Rn. So we apply I will call this double star this relationship. So in applying that relationship we have nothing, actually we didn't use anything about p less than n and so on. So we apply double star with p equals n. So if you go to the proof, we did not have, it's only when we wanted to choose the t such that those two indices became the same, then we tumbled on p star, which will imply that p is less than n. Till then we do not have anything else. So you have mod u power t power tn by n minus 1 Rn 0 is less than or equal to t mod u to the power of t minus 1 of 0, and then p dash. What is p dash? So we have p equals n, so instead of p dash we have n by n minus 1. So p equals n, so 1 by p, 1 by n plus 1 by p dash equals 1. So 1 by p dash is 1 minus 1 by n, so 1 by p dash is equal to 1 minus 1 by n, which is n minus 1 by n. So p dash is n by n minus 1, and that's what I have written here into and then Rn, and then you have that mod u 1n Rn. So each of these quantities is less than mod u 1n Rn. There are n of them, and then I am taking the nth root, and therefore I have exactly this. So I have just applied double star with t with p equals n. Okay, so now you have a plus b power t is greater or equal to t times a power t minus 1b, okay, for ab greater or equal to 0. Okay, so use this inequality. So mod u of 0 tn by n minus 1 Rn is less than or equal to mod u 0 n minus 1 n into t minus 1 by n minus 1 Rn plus mod u 1n Rn. So t times this quantity is less than this plus this power t, and then there is a mod u power t here, so the power t can be removed, and therefore you just get this relationship here. Okay, now you choose, now we are at liberty to choose t, so I am going to choose t equal to n, so that I get mod u 0 n square by n minus 1 Rn is less than or equal to mod u 0 n into n minus 1 by n minus 1, that is n again, Rn plus mod u 1n Rn. And all that, of course, mod u 0 n Rn plus mod u 1 n Rn is less than c times norm u 1 n Rn. The c comes because when we define the norm 1 n Rn, you have to take the nth powers of this and then take the nth root at all these, but I also told you that the sum of the norms is equivalent, and therefore you have a constant which you pick up, and that's just dependent on n. So c depends only on n and it is positive. Okay, so you have this inequality, and now you recall that n square by n minus 1 is what? N times n by n minus 1, which is bigger than n. Okay, so this is bigger than n, and therefore by as in previous corollary we have u belongs to LQ for all q belonging to n square by n minus 1, and now mod u 0 q Rn is less than or equal to C times norm u 1n Rn. So that was the previous color. See, this tells you that mod u n square by n Rn is less than or equal to C times norm u 1n Rn, and n square by n Rn is bigger than n. So just as we did in the previous color, for every q between n and n square by n minus 1, we have this result. So this is a bootstrapping trick. So which now repeat with t equals n plus 1. So what do you get? If you write t equals n plus 1, you will get mod u 0. So Tn is n plus 1 n by n minus 1, okay, is less than or equal to mod u 0. Now t equals n plus 1 means you have n square by n minus 1 Rn plus mod u 1n Rn. But mod u 0 n square n minus 1 Rn we already know is less than or equal to, so C times norm u 1n Rn. And then recall that n plus 1 n by n minus 1 is bigger than equal to n square by n minus 1. And so again we use the previous corollary. Therefore, this implies that for all q belonging to n square by n minus 1, n into n plus 1 by n minus 1, we have mod u 0q Rn is less than or equal to C times norm u 1n Rn. So now repeat with t equals n plus 2, n plus 3 and so on, and so each time you will increase a certain interval and it will go on forward so that you get all, so this implies that u belongs to LQ Rn for all q in n infinity. All positive numbers will be eventually covered by successively repeating this argument, and norm u q mod u 0q Rn will be less than or equal to C times norm u mod u norm u 1q 1n Rn, and for all u in d of Rn, and then d of Rn is dense in 1n Rn, w 1n Rn, and this implies true for all u in w 1n Rn. So that proves the theorem when p equals n. So when p, and then as I said, for all subdomains you just have to use the prolongation operator. So example, we have seen CF exercises. We have seen in the last set of exercises that we did, omega equals the wall center origin radius 1 contained in R2, and u of x equals 1 plus mod log mod x power k, where 0 is less than k less than half. Okay. Then we saw that this belongs to u of h1 of omega. Now what is h1? h1 is equal to w12 of omega. So p equals 2, it is also equal to n. So you have u in h1 of Rn, okay, which is equal to w1n of Rn, okay, n equals 2, and u is not in L infinity of Rn because it blows up near the origin. So, it is unbounded function, and therefore, you do not have that it is in L infinity. So, the result is sharp, you can only get from for all. So, you only have W1n Rn is contained in LQ of Rn for q belonging to n, and infinity is excluded. Okay, so that proves the result. So, our next thing is to look at p bigger than n, which we will do next time.